Hello again. This is the second part of a three-part video on C++ Type Erasure and understanding it through the implementation from scratch of std_any. I moved here because I was freezing in the shadow. Here there's a bit of sun, so it's keeping me warmer. Okay, let's proceed now to implement this toy version of std_any. How do we start? Well, we simply start with defining a struct called any, and then we have to fill it in somehow. The first thing to think about is that we want to initialize any from any type, so surely we need some constructor that takes a t, and that t should be anything. Should be anything means that we could naively think of templating the whole class. After all, there's so many template entities in standard libraries. There's stud vector, there's stud list, stud set, and so on. But that's not actually leading us far, because just like I have defined here an any starting from a foo, I could define another one called g and initialize it, starting it from a bar, which is another type I've defined, and type that doesn't contain anything. But these are actually different types. This is any of foo, and this is an any of bar. So I can't even do anything as simple as this, changing my mind and saying, oh, I want actually to put whatever is in G, I want to put it in F. It doesn't work because G and F have different types. So that's not gonna work. That means that we don't want any to be actually a template class. We want it to be a class. And so if this must be any type, if this t must be templated, that means that it's like, if that t must be able to be any type, that means that the constructor must be templated, not the class. And so this is one first step. And fair enough. Now, surely we want to put this t here, this payload, somewhere inside of this object. And but we don't have the type t here. Like, we can't do anything like this because the type t is scoped in the constructor. It's just available here. We don't have the type t here. Also, we don't know base classes of it, even because t could be literally anything. We could initialize any from an int. Int doesn't have a base class. So there is no type that we know of that we can put here, except for one. The only type we can use to refer to some object of which we don't know the type is a void pointer. We can have a pointer to void, which means something that can point to any object, including whatever t will be instantiated to. This at least is a kind of a viable approach, and we will then later see whether this approach is used or not by the standard implementation from GCC. But yeah, let's say that this is a good decision for now. How do we initialize it? Well, surely we want to initialize it in the constructor, but how? Like, what we put in here? It is a void pointer, so what we can do, like, it's the void pointer, it's not the object itself, so that means we need to put the object somewhere else, and then that void pointer will have to point to it. One way of doing it is to allocate space on the heap by using the operator new and saying, I want to create a new object of type t, copying it from t. And this will create the object on the heap and give us back the pointer to t, which we cast back to pointer to void, and so we have it in our class. Good. This starts to make a bit of sense. So let's say that everything is fine so far, and let's just look at what else fails to compile. As we see here, what fails to compile is any cast, because we haven't defined it yet. So let's start defining it. Oh, incidentally, I forgot, but most likely I want payload to be a private member of the class, so that we don't expose things to callers. And let's start defining any cast. As per the standard implementation, this is a friend function. And what does it return? Well, the any cast is the way for the caller to say, I know what type is in this any, because I keep track of it, and And so I'm telling you, this is the type in there, please give me the object inside of this any, assuming it's this type. That means that it is a template, it is a template function that has so the caller provides t as a template argument, and that is the t that it gets out of the any via this any cast. And I'm returning by reference just because that's a possibility. That's not actually how the standard version is implemented, I believe. That returns by value, but we can do one way or the other way. It's just a design decision. In this case, I'm returning a reference. And how do I return that? Well, we have the any that we want to take the inside of. So we do any dot payload, and that's a void pointer. So that's the payload, the pointer to the payload. What can we do with it if we want to get out a reference to t? Well, first we can static cast it to the type that the caller is requesting. So, to a pointer to the type the caller is requesting. So in this case, tconst pointer, and then we dereference it to give out of to the caller the actual reference to the t inside of the any. And this is fine. What this is complaining here, what the compiler is complaining about is actually this line here, where I'm using any cast to modify the inside of the any, and that's not possible with this overload I've just written because this takes a constant any and returns a constant reference to that. But we can just write another overload, which takes a non-constant any and returns a non-constant reference to t, and so it has to cast to a pointer to non-const t. Fair enough. What happens now? Well, first of all, we can start commenting out a few things. We haven't implemented everything, so something would not compile down there. But let's see if whatever we've written so far does any sense, makes any sense. Well, in reality, we already have a memory leak, and it says that we're leaking 4 bytes of one object that is being allocated on line 31. Well, by the constructor on line 13, but the actual object is being created on line 31. So if we go there, line 31 is precisely this line. We have a memory leak. Why do we have a memory leak? That's simple. We are creating an object on the heap by a new, but then we are not deleting it by a delete when it goes out of scope. How do we solve that? Well, we need a constructor. Destructor, sorry. We need a destructor. So let's start defining a destructor. And what do we do in this destructor? Simple. We call delete on the payload, and that's it, right? No, it isn't, because payload is a void pointer, so it doesn't actually know what object it is pointing to, and so delete cannot be called on this pointer because delete needs to know how big the object is in memory in order how it is made in order to actually be able to delete it. Whereas that's not possible if we have just a void pointer. So somehow we need to cast this payload that is a void pointer to a pointer to t before doing delete. But we don't have t here because the t is up here. The t has been erased here. This is what is erasing. We're allocating space on the heap for a given type t, but then we are storing it as a void pointer. So this is the erasure. But now we need to do the recovery of that type in order to be able to delete it correctly here. But the only place where we have the t available is precisely the constructor. So what we can do is to say that in the deleter here, we don't want to call delete. We want to call some function that needs to be initialized by the constructor. The constructor needs to initialize the function that takes care of deleting the object in the destructor. And just because I'm saying that the function needs to be assigned at construction time, that means that the function cannot be a member function or a free function. It must be a pointer to a function. And that pointer is maybe initially null or whatever, but then the constructor sets that pointer to function, to the actual function that should do the deletion. So let's think about what the signature of the function should be. Well, of the function pointer. Well, a function pointer is normally defined with declared like this. You have the return type, then you have parens star, the name of the function, let's call it delete underscore, close parens, and then open parens and the parameters. Okay, that's generally how you declare it. And what is the return type? Well, this is a deleter function, so it doesn't return anything, it just needs to call delete. And what about the parameters? Well, because we need to call it here, it must take the void pointer. And actually it can take a pointer to void const, because deleting can be called also on a constant object. So this is the type of this is the pointer to the function that needs to do the deletion, and that's the function we need to use here. But the question is, how do I initialize it? Where do I initialize it? We've already said that in the constructor here. But how? Like what is the initializer for this thing? Well, we can just use a lambda. We can just use a lambda that takes this void const pointer p. P stands for payload, and inside the body we just call delete p, right? Not quite, because we're back to square one here. We cannot delete void, but that was the point, right? We wanted to do it in the constructor because we know the type t. So what we can do here, what we couldn't do in the destructor, we can do in the constructor, which is we can static cast the pointer to the correct type of the pointee. So we do this, and now the destruction should be dealt with correctly. Let's try to compile. As you can see, I didn't say earlier, but I'm compiling with this flag here, f sanitizer equal leak, that detects the leaks, and that's why earlier we detected the leak. As regards what I'm printing here, that's just how I've implemented foo and also the type bar. They basically, foo contains an int, bar doesn't contain anything, but both of them have the special member functions saying things that they're doing. For instance, this is saying I'm calling the constructor with the int2 and I'm creating the object of this address. And then this is saying, oh, I have this object of this address and I'm copy constructing another object which has this address, and so on. This is just in case something goes wrong. This could help us understand what is going on. But most likely we will not need to care about that. So let's see what else happens if I uncomment the stuff. First of all, there's still something that doesn't compile because I haven't defined the function has value. The member function has value, so we can start doing that, and we can do it here. It is a function returning bool. It is a constant function because it doesn't need to alter anything, and it can just return the payload. The payload is a void pointer. Well, it's a pointer in general, and so when the pointer is null, it will be converted to false. If it is not null, it will be converted to true, and so it's doing what we want. Let's see if this compiles. Oh, right, it doesn't compile because one of the tests is an attempt to create the empty any, and we haven't defined that yet. Actually, we have defined this constructor, which is not viable for default initializing, so we need to define a default constructor. So we can do it like this, and what happens now? There would be tons of errors because we haven't implemented anything yet, but we can already start seeing something. For instance, we see that the error here is on line 25, and what is failing is this assertion here. And I can actually already tell you that if I change the assertion to, say, 4, this will pass, and something else later would fail. And I will tell you now why. Let's go back. What was the number? 55. Okay, the line is this one. Now I'll tell you what is happening. At this point in the code, we have both the object f and object b of type any, and these two lines are telling that both of them contain a foo, and that those foos could both contain an ei that is equal to 3. Then this line is using that mutable version overload of any cast we've defined to cast b to a foo, because there is a foo in there, and then we are taking the I out of there, and we are assigning the number 4 to it. And then we are expecting that B to have the 4, but the F to still have the 3. But the assertion just failed, because in reality this F also contains a 4. And so the point is, if I changed the inside of B, why does the inside of F also changes? That means essentially that the default copy constructor, because let's look at where B is initialized. B is initialized here from F. F is an any, and B is an any. So B is being default initialized from F. And so the default copy constructor is being called, which does a member-wise copy of everything, and so it is also copying the payload, which is a void pointer. So what you end up with that line, after that line, is 2 any objects that have a payload void pointer pointing to the same location. And that's why changing one is changing the other. So what we should do here really is defining a copy constructor, but we should have already known that. When you start defining even just the destructor, then you should define all of the special member functions. That's the famous rule of 5. I don't remember. Yeah. Anyway, if you define one of those special member functions, you're better define all of them. So that's something we should do. I also have to, before going there, I have to mention another aspect. And the fact that I've basically written these two anycasts overload without much care, in the sense that the caller passes a t as a template argument, and this line is just assuming the caller is correct. And so if the caller has indeed given the correct type, this will work fine. If the caller has given the wrong type, this will invoke undefined behavior. That's not the specification of stdny. What stdny should do instead is to actually check the type and verify that the caller is requesting is the type that is stored inside the any, and throw an exception if that's not the case. That's something we can do later, because it is similar to other stuff we also have to do. So to do, throw, and that's the case here and here as well. So let's go back to the idea of writing the special member functions, because that also is the opportunity to give. We've already seen what type erasure is here. We've already seen it because what we've done is a line here that does the type erasure, that forgets about the type, and then a line here that puts things in place such that the type can be remembered. Indeed, it means that somehow this delete underscore, we make it point to a function, which is the body of this lambda, to this lambda, which has an interface that does not depend on t, because it takes a void const pointer and it returns void. So the interface of this function doesn't refer to t, but the body does refer to t. So the body is what is keeping track of the actual type of this object. So this is where the recovering of that, like the lambda is the place that recovers the type that was erased here. And now we need to do something similar. Why do we need to do something similar? Because we're writing the copy constructor, right? So if we want to make a copy, we want to surely to make a copy from the payload of the other object and to the payload of the object we are creating, but we don't want to copy just the pointer. This is exactly what is happening by default, and we don't want this. We want a bare copy for delete underscore, because delete underscore is just a stateless function that takes a void pointer and deletes it. So the object we are copying from and the object we are creating have exactly the same way of deleting their object. So that is because they will contain, the two any's will contain the same type. So it makes sense that we use the same deleter. But as regards the payload, a real copy needs to be made. But we can't make a copy here because this is a void pointer. You cannot copy an object if you don't know its type. So again, what we need is initializing a cloning function here, just like we've initialized the deleting function. And so how do we go about that? Well, we go to down here where we've defined delete, and we just define another function. We call it clone underscore. this one though, because it has to essentially make a copy of an object, it needs to return not void but a void pointer, so a pointer to the object that we are going to create on the heap. And now let's go back up here in the constructor and say that we want to initialize that, and we do clone underscore, and we initialize it again with a lambda that takes a void const pointer to p, but it returns a void pointer. And the body of this thing needs to do return, and here it needs to create the new object. Just like we've done for initializing the payload here, we do something similar here. We want to initialize a new object of type t, and this new object of type t needs to be initialized from the very object that this payload p points to. So how do we go about that? We need to dereference that void pointer, but before dereferencing it, we need to cast it to a non-void pointer, to the thing we know. So we can dereference what? A static cast of t const pointer of p. So here we are taking the p, which is a void pointer, static casting it to a pointer to t, because t is available here. We are in the constructor. And so we get back a pointer to const t, we dereference that, so we get the actual object of type t, and then we are allocating on the heap another object by copying that one. So this is okay. Let's see what happens. Many things would not even... something compiles, fair enough, but... we haven't really done much here. This is just a copy constructor, but we need to implement other things. I'm even surprised it even compiles, but like we know the job is not done here, in the sense that we've defined just the copy constructor, and we want to define also the move constructor and the other member functions. As regards the move constructor, oh, and now, sorry, one thing I was forgetting, now that we have the clone pointer to function, we also want to make sure we copy that one when we copy over an object, because again, the cloning method is the same given a t. So if I'm copy constructing an object of type any from another object of type any, the way of deleting is the same for both of them, and the way of cloning is the same for both of them. But, oh yeah, the obvious thing I forgot is that this is where I want to use the clone method. Like, I want to say that the other object needs to know how to clone itself. So this is the clone method called on the payload. And so the payload of the newly created object will point to a new, like a brand new copy of the pointee of the other object. As regards the move constructor, it needs to do something way simpler, because it doesn't need to do the actual copy. We want to steal the resources, so it just really takes the pointer of the other one. But a critical bit here is that we don't have to forget to basically set to null pointer the other one, because we want the left hand side, well, the newly created object to have stolen the payload of the right hand side. And so we need then to say, actually, the right hand side doesn't have anything anymore. And this is one thing, but that's not finished, because at this point, the right hand side would be an empty object. We've removed its payload, we've set its payload to null pointer, but when that object will go, well, we could still copy over that empty object. And if we copy over the empty object via a copy constructor, then that would call this one here, and which would do this. And if this one is the void point, the empty, the null pointer, then clone would try to initialize with new an object starting. Well, it would try to dereference here, to dereference a null pointer, and we don't want that to happen. So that means that for an empty object, it actually doesn't make... What it makes sense is that the clone method for an empty object should actually just do nothing, and return a null pointer. Like, I haven't allocated anything. Clearly this should be a void pointer. And something similar we can do for the delete method, in the sense that, well, deleting a null pointer is fine, it doesn't happen, and nothing goes wrong, so maybe we can just leave it. Let's see how it goes. What else now? Because we've defined the move constructor, now some other special found member function is not defined, and these are basically the assignment. As you see, there is no assignment operator. Move assignment, copy assignment, we need to define them both. But we can just take inspiration from the move and copy constructor and just change the signatures. So the assignment operators return a reference, and they don't have initializer lists, so we can move them here and just kind of rewrite them as assignments. So we can start doing it like this, and we can do something similar for this one here. Okay, I'm just literally copying over the code, putting semicolons, putting equal instead of square brackets, and then changing the signature. Okay, not sure, yeah. What else? Oh, clearly these are the assignment operators, so this should return the this pointer, both of them. And what else? There's still something left, because the assignments, first, if we are assigning an object to itself, either move assigning or copy assigning, we don't actually want to do anything. So that means that we want to take this route only if the other object and this object are exactly the same thing. One way to check that is that this is not the same as the other object, and we want to do that in this case as well. We could also equivalently saying that the payload of this object is not the same as other dot payload. This is exactly as the other line, like this line here and this line, as fundamentally checking two different addresses, but that should in both cases be the same. So we want to avoid this, but there is one last thing we have to do in this like assignment operators, and you would realize that with weird errors, or with leaking errors, if you forget that. And actually maybe I can do it. Well, this is just failing for another reason, but I can comment out some things. For instance, this is theoretically this is doing move copy assignment or stuff like that, so I can comment out this stuff, and now you should see some leak, and it leaks for objects allocated on line 83 and 91, and 91 is here and 83 is here. And the reason why that is happening is that when we assign an object to another one, we should first get rid of the object to the left hand side. We should destroy that. So that means that we do need to call delete here on the payload before doing any job here, because we're assigning something to something else. So we should first delete the left hand side before copying or moving over the stuff from the right hand side. So let's see if this indeed doesn't fail anymore. So that was the reason for the leak. And now let's uncomment this stuff, and let's see how this goes. This is failing on the has no value on line 119, which is here. This has just been default initialized, and it does have a value. That's weird, and the reason is fundamentally that we've forgotten to initialize the payload. So this is just a random pointer value. If you put it to null, then maybe things will work. Well, they work better, but there is still something that doesn't work. And how can we find what is going on? Well, does it tell us where like what line is failing. No, but we can analyze it bit by bit. Well, we can actually, yeah. Let's see. Let's comment out a few things here. So we have just these 5 lines. Let's see if something in there. No, everything seems fine in there. So let's comment out from this line down. We're just splitting the code and trying to find where something causes the failure. Everything seems to be fine here as well. And what about this? I'm just literally doing kind of a bisection method to find where something went wrong. Oops. For instance, what if I comment out this? Still good, so it's really on the last lines. And most likely, will this be enough? No, this is good as well. So what is failing is literally is it the hash value? No, it's actually, it's not because of the assertion. It's literally because of the copy. It is this copy constructor here that is doing the wrong thing. Why is it doing the wrong thing? Well, can we step through the code to see what happens? Yeah, maybe stepping through the code is actually the good thing. So let me compile it with that thing in there, and let me put a breakpoint here, and let's step here. What do we have here? Well, this object here is the empty object. It does have no payload because we're default initializing it here. And then we're trying to copy construct it. Where do we go with the copy constructor? Oh, we already know what is happening here. The other object is empty, so it has empty the payload, but also doesn't have a valid address for delete and clone. And so clone here is calling some random address. So that is what is going wrong. And the reason why it is going wrong is that, am I in another file? Yeah. The reason why it is going wrong is that we should do this even for empty objects. So maybe. So what we can do is that we copy this one here, and that's how we initialize the clone method. And let's see how it goes. Still wrong. Yeah, still wrong. Why is that the case? Maybe we want also to initialize this one here, the deleter function with a function that does nothing. Is that the case? Yes, that's because otherwise, well, it's fundamentally the same reason as before. When the object is empty, the delete function pointer for an empty object was left invalid, and so this function call was failing. Yeah, so now everything seems to work, and so yeah, that's a very basic implementation of STD. Oh, wait a moment, I forgot that we should make a kind of runtime representation of the type available here for the compiler to check that thing. So again, where the compiler knows the type is in the constructor here. So we should probably have something like this initialized with some type information. For instance, type ID called on the type T, and type ID will just provide some sort of type ID, I think it provides a type info, I think, and we're calling it type underscore. Does that work? No? I absolutely had to come back home because I was freezing, and we were left essentially here with me trying to initialize an object of type std type info from the output of type ID run on the type that is available here in the constructor, but that fails because type cannot be initialized from there. It just doesn't have such a constructor, and we could actually go look into it and see delete doesn't have a copy constructor. that's what it is. Doesn't have a copy constructor, or it has it deleted. So one way to face this is to just have a pointer, a constant pointer to such a type, and that gives us the opportunity to also have a null state, which is appropriate when an any is empty, right? So the type ID doesn't make sense if any is empty. So what we can do here, therefore, is to say, actually, as far as copy constructor is concerned, we are still just copying the information from one to another. We do the same for the move constructor, but then for the move constructor we want to leave the other type empty, like the type of the other object empty, so we have to put that to null pointer too. And then we want to do the same in the move constructor, move assignment, sorry, here, and also, but before doing that, we want to copy that other type from the other object, and we do this here and here, and so this should be all okay. Everything should compile and run as previously done. It passes, and but now we can actually write the exception code, well, not exception, the code here that throws an exception if the types are different. So what we do here is that we say we consult, we inspect, we look up the type underscore field of A, and we check that it's not, if it is not the same as the type ID of the type that the caller has passed, actually its address, then we have to throw. Otherwise we proceed as before. Now there is a bad anycast somewhere, but I haven't included that header, so I can just do a logical error saying bad cast, for instance, and we can do the same in the other throw. This will clearly not do anything so far, but if instead I go here, for instance, and I know that there is an int inside of D, and instead I try to get double out of it, then I will get the bad cast exception that I've thrown. And so this makes those two functions, anycast, more compliant with what the standard library prescribes. So yeah, this was basically a very basic skinny implementation of std_any, not particularly not performant at all. I've not thought about performance in any way, but at least it it has been the excuse to show how type erasure works. And so just to summarize, the type erasure is the act of erasing the type, but is also the name of the whole technique that consists of erasing the type and recovering the type. And as far as any is concerned, or actually any type erasing class will essentially have a constructor that is templated in such a way that it can accept everything. I just realized that I forgot to actually use perfect forwarding. Everything works, but we are making more copies than we actually need, in the sense that when we are passing a temporary, we are actually here making a copy of that temporary rather than temporary, or if you want, R value. We are not stealing the resources, but we are just making a copy. So the way to deal with that instead is to oh, and this means that I've forgotten other bits as well, and this is actually interesting now, because everything seems to work so far, but if you how do we understand this? Yeah, one way to look at it is probably this. Let me do this. Let me initialize a foo here, and then we move it into here. Oops. Move into here. Now, this means that we are creating an object of type foo here with the 2 in it, and then we are moving it into the any. So what we would want is that any takes ownership of the actual object foo by moving the resource into it. But that's most likely not what is happening here because of the mistake I made up there. And indeed what we can do is that we can put a breakpoint here, compile the code, and then run the code and see what happens. So foo is the object with the type with the number 2 in it, and it goes here, and we have the t, and this t as the value 2. So the object, the foo that we've created, has been moved into this t, but then at this point we don't move it again. So that's shown by the fact that if I step to the next thing, that this object has been initialized now, with at least its payload has been initialized. So we have run the copy constructor of t, but the t here still has the same value it had. So we moved the foo that I defined in main inside this parameter here, so that was moved, but then this is not being, this is where the copy is happening, and that's not what we want. I can actually for a moment rerun just to make sure we are on the same page, which is that foo, the address of foo, oh yeah, I'm printing here what is, I'm printing here what is happening. So this is the object we've created. Then we step into here, and this is the move constructor. So we are moving that very object that was created inside another object. We're move constructing the parameter of this function here. Indeed, if I go here and print the address of t, oh no, sorry, how do I do that? Print address of t. Yeah, it tells us this address, which is other than those zeros, it's this one here, it's this very address. So that means we've moved the object that was defined in the caller, in the main, has been moved into this t, and then, and payload for now is a random address, as you can see here, the payload of the this object. But as soon as we go to the next step, we have allocated something on the heap. So we have made an actual copy of, this object here, and indeed the copy constructor has been called here. We are copying that foo into the heap. So let's see how things change instead if we employ perfect forwarding, which means that, well, first means that it's better if I go here. The reason being that the change will be less trivial than we think, because as soon as I put the universal reference here, a bunch of compilation failures happen. Surely we know that when we pass t here, we want to do std forward, and that's the whole point. We put forwarding reference here so that we can forward with the correct value category. So an R value in the caller is passed on as an R value, and an L value is passed on as an L value. Perfect forwarding. But we have this error here which says cannot allocate reference of type bar ampersand. What is that, and where is this coming from? Actually, this tells us that the error is on line 106. If we go to 106, it's this line here. So, and this line is trying to copy a bar, to create an any from a bar, but the point here is that this left-hand side of this declaration, this right-hand side of this declaration is an L value, is a non-temporary. Because of that, the t here is initialized to that type ampersand. And so we have that type ampersand here, but when you do new, you need the type, not a reference. So we need to remove the reference from this t. How can and the same error is also here. The pointer is giving us the same error. You cannot do a pointer to a reference of type bar ampersand. So the problem here is that on these 3 lines, t is a reference. At least it is a reference when the caller is being given an L value. When it is given an R value, it's fine, because t is not deduced as a reference. But when it is an L value, then t is deduced as a reference. So the solution to that is just to have another type, another template parameter, not to be deduced, but just to be computed based on t by decaying it. Decaying means, among other things, removing the reference. And so here, instead of t, we do td, and the same thing here, and here, and here on the new. And that's it. This should now all work, but we fail, and this is very interesting now. But this is actually failing for another reason, for a Stack Overflow. And indeed, you can see that basically the copy constructor is the templated constructor, like the constructor we've defined, has been called. It's been trying to call itself for 250 times until the runtime says, no, please stop doing this. And the reason for that is not explained here, but actually I think, does this refer to the function main anywhere? No, it doesn't, but 17 is just the constructor. But we can simply go back to the code here and do what we did earlier, which is comment out things and see when something fails. So probably this is fine. This is not what is causing the failure, but I know where the problem is. So you could basically just uncomment out the statements until you find what is going on, and this is what is going on. I think this should cause not this one. Well, this one should cause the problem. Yes, indeed. And this is the line that is causing the problem. Why is it? Because this is an any, and we're constructing an any from an any. And what is happening is that the best constructor that is matching is actually this one. Why is that the case? That is the case because this line is constructing an object of type any from an L value of type any, a non-temporary of type any. What does that mean? It means that we would want this to be called, but to call this, the compiler has to add the const. So it needs to convert the right-hand side to a const. It has to put the const on there in order to call this. So it's not the so it is a possibility. But this constructor here instead is matching much better because t is instantiated to any ampersand, and so this turns out to be just any ampersand, which doesn't need to be the constant to be added in order for be a match. So this is actually a better match. It is a better match, and what it ends up doing is that it is a better match with t being any ampersand. So td is any without the ampersand because it's decayed, and this thing is trying to copy the any. And what does that do? Well, it calls back again this one, and so you have this infinite recursion, like the constructor infinitely calling itself. And the way to deal with this is to do requires and to put a requirement here and say that you don't want the type td, so without the reference, to be the same thing as any. If they're not the same, then yes, we want to call this. If it is the same, don't call this constructor. And clearly the one that will be picked up is this one. And now if we do this, it works. And now we can go back to the idea, oh, I've left all of this commented. We can just uncomment to make sure we've not broken anything. Okay, fair enough, it passes. And now what we can do is just to go back to see what happens at this one in terms of stealing the resources. So we construct the foo, and we see that the object is created with this address. But now we step into here, and well, there has been no copy. We've not jumped into the no copy nor move. We've not moved this object inside the parameter because the parameter is a reference, so it doesn't need to be copied. And that means that t here, if I print it here, t, well, I mean, this does tell us the address, so it's this one, which is, well, you can read it, right? It's 7 and then FFFD8C. So this t is precisely the same object as the caller because we're taking it by reference. And now that it's being taken by reference, then it is being cast. This is std move, and then it is being moved. This is the move constructor. Now that the very object is being moved into the heap. Yeah, so that was it. Yeah, so everything seems to be working, and I hope this clarified, not this last step, but the whole video clarified what type erasure is. So a class that uses type erasure, that type erases other objects, has to have a constructor that takes that is templated so that it can accept any type. Then it stores the actual type through another type that is, let's say, less specific. In this case, void pointer is being used, which is the least specific type pointer you can have. But at the same time, in the constructor, which is the only place where you have the type, the actual type of the object available, you also want to initialize all the APIs that need to know about the type t. And the point of these APIs is that they have an interface that does not depend on the type. For instance, they take void const pointer here, and this one returns void pointer, but their body, their body here does depend on t, and the same thing is here for this body here. This way you have the erasure of the type here and the kind of recovery of the type here. Recovery just means initializing in the constructor that is aware of the type t those functions that you will need to use in places where t is not available anymore, which are the copy constructor, where you need clone, the destructor, where you need, where is the destructor, where you need delete, and also the any cast in this case where you need the type. And yeah, so I hope you enjoyed this video. I hope it helped you understand what type erasure in C++ is. And in the next video, the third part, I will put this code side by side with std_any and look at the similarities, differences, and when I will make a few more comments. Thank you very much. I hope you enjoyed this, and I hope you will join me for the next video as well. Thanks. Bye.